many of you are security engineers or the designated security person in your organization? Okay. And how many of you are cryptographers, cryptographic engineers, can spell AES? Okay. So what we're going to talk about today is a little bit esoteric. It's not specifically related to Android. It's something I worked on for 6 years. And it's kind of an interesting side avenue into security. Basically what happens is we'll talk about kind of what the background is, some very basic things about cryptography, how to encrypt data in a way that's secure. I won't be able to do the demonstration tonight. And then I have some additional information about how to misuse cryptography in a way that looks perfectly reasonable. So this is probably very familiar to you. The concept is you have that's useless. You have something you want to protect. Inside the red box is your protected area. You have some important information that you're going to convert into a ciphertext so that you can export it to the rest of the world without worrying about whether or not the channel you're sending it over is protected. So when you send your credit card information, SSL, I'm sure you're all very familiar with this. And there's this side channel that can happen. So because cryptography has to run on hardware eventually, and because hardware uses electricity, and because transistors use different amounts of power depending upon the data that they're operating on, you will have leakages. The question is, how do we control those leakages in a way that doesn't give the adversary enough information to extract the secret key or the secret information we're trying to protect? So when you have a side channel attack and you've got a strong cryptographic algorithm like AES or RSA or a similar algorithm, and you've done your implementation correctly, you haven't made any mistakes in the way that you use the crypto, you can still have leakages. So this was discovered early and often in the smart card industry, where you've got a small embedded microprocessor. In the early days, these things were literally 8-bit microprocessors, like a PIC microchip. And you could literally defeat the security on these things and turn them into money. How many people have ever looked at the internals of AES? Okay. So before I started looking at this years ago, I thought, wow, these crypto circuits, these crypto algorithms are really complex. It turns out that the math is pretty complex, but they can be broken down and implemented in a way that's very straightforward. AES was designed so that it could be implemented on an 8-bit microprocessor and still have reasonable throughput. Now, no, you're not going to encrypt the Library of Congress on a Z80 and get any kind of a reasonable response. But you can encrypt a few packets at a time, and you can do some very reasonable things with a very lightweight microprocessor. At the same time, with an x86 processor, you can get tens of megabytes of data per second without really putting that heavy of a load on the CPU. So the way that the implementation works is you've got an overall black box. The black box is made up of steps called rounds. Each round has steps inside of it. Each one of those individual steps is very simple, very straightforward, and if you're given the input and the output, you can easily figure out what goes on in between. But when you put all of the steps together and all of the rounds together, you have a secure function. So what a side channel lets you do is to break apart the security of the whole and look at individual substeps within individual rounds. And if you can do that, then the security of the system is basically broken. So to give you some background on AES, it's a symmetric cipher. What that means is, if I want to exchange a key with you, that has to be done over secure channels. So I have to hand you a piece of paper, or I have to have someone deliver it to you, or over some kind of trusted connection. This isn't going to work real well for e-commerce, but it works pretty well when you want to encrypt something, store it away, like on a hard drive, and then recover it later on. And it also works well in a situation where you want to encrypt a large set of data and give it to someone that is only going to be able to decrypt it when you provide them with the key later on. It has some options about the size and the number of rounds. And there's some things you need to know about AES. If you use the raw AES mode as it is, you can get yourself in a lot of trouble very quickly. The key to it is not to just take the building block and plug it onto your system, but to combine it with other steps in the right way so that when you're done, the system from end to end is secure and protected. And there's a lot of information here. There's a lot to understand. The Wikipedia page is actually almost completely accurate and gives a very nice explanation of how it works. Just to give you some ideas about what we're looking at, this sub-byte step, so these are the steps within a round. So you're going to go around the circle 10 times. This is an 8-bit lookup. So there's basically a 256-byte array, and you just do a 1 character at a time lookup, byte for byte. This one stores the 16 bytes of the state, and then you just shift rows a certain number of characters. So it's essentially a memory move. Or in hardware, it's just changing wires. Oh, I'm sorry, I put that one in twice. This one is a little bit more interesting mathematical function. It mixes up the data and provides a nonlinear characteristic. And then this one is just an XOR function. It's a byte by byte XOR function. So, I mean, anyone in the room not know how to implement an XOR? Right, so the point is when you break it down into the individual steps, each individual step is very easy to implement. And by the way, how many people think that using an XOR with a secret key makes a good secret cipher? Right? So in and of itself, it's pretty bad. But when you combine it with the other steps in the right way, you get yourself a very strong solution. RSA, Diffie-Hellman, a lot of other solutions use a public key, private key to get over the problem we talked about later, which is the issue that if I want to exchange something with you, I don't necessarily want to have to exchange the keys in a secret environment. I don't want to have to drive to your house and give you the key before we can communicate safely. By the way, depending upon how paranoid you are, you shouldn't give somebody a secret key over the phone. So you can actually put your secret key on a key server, and I'm sure everybody's done this at some point. Other people can download it, and then they can decrypt it securely. So as long as you know that that key goes with that person, then you can download their public key, decrypt the data, and you've safely communicated information. Now, one thing to be careful about is you have to be sure that their public key belongs to the person you think it does. There's a thing called an SSL man-in-the-middle attack that basically substitutes an independent public key for the one that you think you're getting, decrypts your data, and then re-encrypts it with the other end's key. So you have to watch out for things like that. So this is a slide that shows what happens when you do a cryptographic operation on an 8-bit microprocessor on a smart card. And you say, well, why do I care about this? I'm using Android. It's a 32-bit microprocessor. Well, this shows it a little bit more clearly, but as I'm going to show you later on, even on an Android phone or an iOS phone, you're still going to get a certain amount of leakage. So there's some interesting things here. You can see that the power consumption is at a low level here during the input phase. Something happens in the middle. There's an output bump here that takes place. Some more input. And then the cryptographic operation ends here. But wait, there's more. You also get the EEPROM. So the EEPROM write takes a considerable amount of information. And by looking at this, you know whether or not you're writing zeros or ones. So if the security of your system depends upon people not being able to detect what's being written in the EEPROM, in this case, you've already got a leak. OK, so the question is, yeah, there's a difference here. Yeah, there's a difference between a 0 and a 1. And how do I know if it's a 0 or how do I know if it's a 1? So a standard practice is to get an example of the device and then do some tests on it and watch it. And then you sort of learn how it operates. And it tells you what the signature is and gives you some feeling about how the thing operates. So you may know from, I'll get right to you. You may know from having bought a PIC, let's say that you know that the smart card is implemented using a PIC microchip. Or maybe you can even get access to the card. By the way, SIM cards have the same vulnerabilities. They're basically the same technology. So you get a hold of them as a developer, get some samples, run your own code on it, and then watch it operate. The other thing is, if this is a secret, and it goes like this when it's a 1 and that when it's a 0, or if it's just the opposite, how many times do you have to try? Right? If you know for sure that every one of these bits is either a 1 or a 0, and you only have to try twice, that's not very secure. OK, so there's two questions. The first question is, sounds like I have to have physical proximity, like I have to physically have the device in my hands. You have to be at least in the same room as the device. And I'll explain more about that later. The second question is, what about these EEPROMs that are advertised as secure? A lot of it depends upon what you mean by secure. A lot of times when they say secure, what they mean is cryptographically secure, unless they say explicitly power analysis or DPA or SPA secure, then they're probably not. They're probably not. Experience indicates that most cryptographic devices, unless they are specifically designed to prevent this kind of an attack, are vulnerable to it. So the question is, could the battery management system, so the onboard power measurement system, be used in order to exploit this kind of an attack? Maybe, but probably not. And the reason why I say that is because the clock speed is typically too slow. Usually the clock speed on those things is measured in kilohertz. And to do this kind of an attack, you typically want to have a sampling rate about 10 times the speed of the CPU clock cycle. Although that's not always the case either. Turns out sometimes, one system I worked on, we actually had to filter out everything that was greater than 10% of the CPU's clock speed. So it was a CPU running at I think, 10 megahertz. And we got our best signal when we filtered everything above 100 kilohertz. OK, so the question is, what's the scale of this graph? So this device is this particular device is an 8-bit microprocessor. It's running just over 3 megahertz. And the sample rate, I think the sample rate is something like 100 megahertz. But you could probably get away with about a 30 megahertz sampling, like a USB sampling scope. I'll get to that one. That's a good question. The question is, is this being done wirelessly? This one is a wired attack. So what's happening here is maybe I should just go on to the next slide. There's a cryptographic device, smart card. We put it in a fixture, and we put a resistor in line with the power supply, like a 10-ohm resistor. And then we put an oscilloscope across the resistor. So what we're measuring here is the instantaneous power consumption through the power supply wire. In theory, you could do the same thing by intercepting the battery in your Android phone. But there's actually a much more interesting attack, which I'll show in a little bit. So this is an example of a wired attack again, also on a microprocessor. And you can see that there's some information here. There's some peaks here, some smaller peaks here, some valleys. And here's the implementation. So the way that this RSA decode works is it goes through every bit in the key. And for every bit, it does a square. And this is in this case, it's a 1024-bit square. And then if the current bit is a 1, it also does a multiply. So it turns out that squares and multiplies take different amounts of power on this system. And in a lot of implementations, they do. It turns out that in the Android implementation, that's also the case. They basically used an implementation very similar to this. So that's kind of an epic fail for the standard library. So what happens is you walk through this, and you look for You look for an operation that takes a different amount of power, whether it's a 1 or 0. And so you see that if there's a square followed by a multiply, that's a 1 bit. And if it's a square followed by a square, that's a 0 bit. So you just read out the bits. And this takes one operation. So essentially, in the time it takes to do one RSA decrypt, you have the entire 1024-bit secret key. This is something else that's a little bit interesting, too. You've got squares and multiplies. So you have a platform that's done the operation. It's a little bit harder to tell based on the height difference, whether you're looking at a square or multiply. But it turns out, in this loop, this if statement doesn't take 0 time. Also, this loop return statement doesn't take 0 time. Right? So there's some time difference. Whether or not this then part gets executed or not, even if the squares and the multiplies take identical amounts of time, there's going to be a different gap. I'll be right with you. So if you look at the difference of this gap, square, multiply, square, square, there's the difference. That's enough to tell you. Turns out you can write a Python script and extract the secret key automatically. Yes, ma'am.
So you need other data to really
So the question is, you're given this set of data, and you're just looking at it, and it's just kind of a jumble of information. You don't really know how to extract the key. So it turns out there's been quite a bit of information published on this. And part of what happens is you train yourself. You look at devices, and you start to develop a set of patterns. You say, well, if I see this kind of thing, where I've got, for example, in AES, if you're looking at a power trace and you see some random stuff, and then you see an operation that has 10 peaks in it, and then you see a bunch of random stuff, or maybe you see some low level, 10 high peaks, and then some low level power consumption, and you happen to know that the thing's using AES 128, which is 128-bit key, which has 10 rounds, that's a pretty good clue that you're looking at the AES operation. So let's take a quick look at that one and see what's happening. And that also tells you where the beginning and the end are. The other thing you can do is get examples of the device. And there's actually a type of side channel analysis called correlation power analysis, where what people will do is get a device that's as close to identical as the one that they're attacking, but they'll modify it or somehow tweak it so that they can insert their own key. And then what they do is they just take the power trace of the device under attack, and they take the power trace of the one that they're using to compare it, and they'll just keep tweaking the key bit by bit until they get an exact match. And when you've got a match and you've got 100% correlation, then you've got the key. So that's another trick in the bag. But a lot of it is sort of experimenting, seeing devices that are similar, training the operator. And there's been some very interesting research done lately about how to automatically, based just on the data and the type of cipher you're looking at, without any human intervention, just go through and figure out what's the right way to attack the device. So in the previous slide, what we saw was you've got a device, it's got a fairly gross power leakage. That basically means that the designer either wasn't thinking about side channel attacks or just made a terrible goof. It's possible, if you take statistical samples, that when you're looking for the value of a specific bit or a specific byte at a certain place, that it's going to be impossible to just eyeball it and say, well, that's a 1 and that's a 0. Like if you look at these power traces and you're trying to figure out which one, it's not going to be very easy to just figure out by eyeballing it. But if you put together a statistical method where you take the sums of where you partition the data, take the set of measurements, record the data itself, and then record it along with the ciphertext or the plain text. So the way this works is you have like an encryption engine. You put in some text to be encrypted or decrypted, and you store that off in your server. And then you measure the power that was used along with that encrypted data. You read that from your data collection device, which could be a digitizing oscilloscope or something similar, and store that on the server and correlate the two. Then after the fact, you figure out some way to partition the data sets. So you figure out, you're basically looking for an oracle. I want to say, well, if I could ask this question, is this bit in this part of the crypto 1 or 0 at this moment in time? It's a pretty simple question. If you can ask that question and get a yes-no answer, that's your partition. So for example is in certain implementations of AES, it's done 8 bits at a time. If I can ask, well, is this bit, is this byte this value or not? And I get some blip in the waveform when it is, and I get nothing when it isn't, well, then I've got myself a very effective attack. So let's, I think I'm going to skip that example because I'm losing you. So here's an example of one that was done in hardware. We took an FPGA. There was some bookkeeping and overhead that let us put in transactions. We were able to put in 20,000 transactions in a short period of time. There's a 128-bit AES implementation in this FPGA. So we were able to generate some random data, load the data, ask for the device to decrypt the data, store off the power consumption, basically the oscilloscope traces, partition the data into yes-no sets, and extract the secret key in about 1 minute and 50 seconds. So we're able to extract a 2 to the 128-bit key, basically a 128-bit key, which should take 2 to the 128 brute force operations. And we're able to get the answer within 2 minutes. Small value 1 ohm resistor is used in line, and then you have taps here. You can see even in a hardware implementation, details about the implementation. So this is AES 128, 10 rounds. And you can see that there's some decoupling capacitors on the board. So this is what it looks like. This is basically an uncorrelated guess. And we said, in this case, is the value of a particular byte at this location 1? The answer is no. In this case, the answer is yes. It took about 32,000 encryptions to get enough data to get that clear of an answer. So again, what does this have to do with Android? One of the things that we did was we took an iPhone, pointed an antenna at it. Oh, sorry, here's the oscilloscope. We took an iPhone, we pointed an antenna at it, a simple ham radio antenna, handheld, ran it through an ICOM radio we got on eBay for somewhere between $1,000 and $2,000. It's a kind of like a shortwave radio. Ran it through a GNU radio, which was about $1,000, and then fed the output of that into a scope. So the one we used was pretty deluxe, but you can get USB ones pretty cheap. And we're able to extract the key from an RSA decryption 15 or 20 feet away, depending upon the room. And that was without tuning the antenna, that was without spending too much time productizing the attack. So it's entirely plausible that a determined attacker would be able to take a nice parabolic antenna, maybe buried in the wall, and if they got lucky, extract that RSA secret key that you're using to do your banking or whatever you're working on. Now, granted, there are a few things. The phone had to be oriented a certain way in our demo, but the point is, you think you're safe because somebody doesn't have your phone in their hands, I wouldn't bet on it. Yes, sir.
My question is, in the case where you're remotely doing this demo with the iPhone, is the iPhone running a specific piece of software that you guys wrote for that?
This is being recorded. Okay, I have to be, the question is, was the iPhone running a specific piece of software? So the place I was working for considered themselves white hat hackers. And one of the rules they had was that they would never demonstrate publicly an attack upon a system that was out in the field. So what we had to do was build a contrived example and run that on the phone. And presented it at the trade shows, saying, you know, this is probably not the same way that the native library is implemented, but, and then one of our guys did an experiment and came back red-faced that we had gotten closer than we should have. And that's about all I can say. And by the way, we ran the same test on the Android phone. And so part of it depends upon how the phone leaks. You can get quite a bit of information by just putting a magnetic loop next to the phone. And there's a lot of probing around which frequency do you want to tune in on. But the point is that an adversary who knows what they're looking for and has had time to set up the attack has a pretty good chance of getting what they're looking for. The question is, how is this vulnerability going to cost me money? Well, first of all, I misspoke earlier. It wasn't an iPhone, it was an iPod. So there's no, the Wi-Fi was turned off. There was no 3G connection. So the GSM data format has been broken. It can be brute forced in a reasonable amount of time. So if you've got data, if you're relying on the carrier to encrypt your data, don't. If you've got encrypted, say, network traffic going across that connection, you should basically assume that someone's got a network sniffer on it. You know, so if you're doing a banking app on your phone and you're using a GSM connection, and I imagine that LTE or whatever, it probably has similar vulnerabilities or will be found soon. That's just my speculation. I don't know for a fact, but how long were people saying that GSM was absolutely secure before someone came out and said, it's broken, buddy? I mean, it's really up to you. If they happen to know that you're using a certain app, or if they can trick you into doing it. This comes up in places like when you're doing the, well, here's a for example. How many people have a Clipper card? You know, that electronic tag-in card for the bus where you just wave it wirelessly? So it turns out that that uses an insecure implementation. You can extract the entire secret key by watching the transaction about a dozen times. And it's probably worse than that. But my understanding is that by watching that transaction a very small number of times, you can extract enough of the secret key. One of my colleagues was able to hack the Clipper card and put arbitrary amounts of money on it. So now that's a wireless transaction. You can watch the wireless transaction go by. So use your imagination. San Francisco parking cards, by the way, are completely broken too, but for a different reason. That's just broken crypto. They didn't implement the crypto properly. Does that answer your question?
Yeah.
Okay. I'm not much of a villain. I just spend time thinking about how things break, and I don't know what to do with it once they're broken. So the question is, how much noisier was the Android device versus the iPhone device? We were able to, it was actually a phone identical to this one, the HTC Evo. We were able to put a loop right underneath it, and I'm sure it wasn't optimized. And just by putting it under the phone in the correct place, we were able to get a very clean signal. Clean enough that you could have used a Python script to just analyze the waveforms and extract the key. So one thing about the iPod was that it radiated pretty strongly out through the front glass. So to be completely candid, if you had a phone that had very good shielding, which is probably unlikely because shielding is expensive and it weighs and it costs money, then you might significantly reduce the range. Does that answer your question? Sorry? Well, the thing about the power analysis, about the statistical methodology, is that uncorrelated noise. So if you've got 4 processors and one of them is doing crypto and the other 3 are doing something that's uncorrelated, if you take enough operations, the uncorrelated operations just go away. So what it means is that you've got a little bit more signal to noise ratio. Maybe you take twice as many samples. Does that address what you were trying to ask? So there was a question earlier about what do I do? So in a hardware implementation, you can generate some noise. You can turn on and off devices. You can insert jitter in your system. You can insert random operations. That's one possibility. You can do things like balance your logic. So one way to do it would be if you're writing a 1 in one place, you can also write a 0 in another place. If you're doing an XOR operation, you could do the complement of that XOR in another place. If you're doing, remember the RSA one where it says, well, if it's a 1-bit, then also do the multiply. What you can do is you can always do the multiply and then just XOR it in and XOR the complement of it in, and that will generate some additional noise. What these things do is they don't actually fix the problem. They make it a little bit harder to discover the issues. Another thing you can do is if you can get the noise reduction down to a small enough level, then you can limit the number of transactions, and you can combine these techniques in order to get a reasonably secure solution. So the goal of this part is not for you to go away and now become DPA experts, but to let you know that which crypto library you use matters, how you use the crypto library matters, how many times you let the user or the adversary do an operation matters. So this is why, for example, on a lot of implementations, they only let you enter your password a certain number of times, not just to avoid a brute force hacker, but also to avoid detecting things like minor variations in timing. So I also promised some crypto usage gotchas, and I think these will apply more in a pure software domain. One thing you want to avoid doing is you want to avoid always having the same secret key in every device in every place. So you don't want to have every implementation have the same key. It's pretty clear what this means when you have a physical token. You know, if I've got a smart card, I don't want to have the same secret key in every smart card. In your application, you'll have to figure out how to use a secret based on the device and a secret that comes from another place and combine them so that you have a unique secret in the software for each instance of the application on each device. This will help protect against the kind of an attack that uses basically a dictionary lookup. If you have to, you have to, but generally you don't want to do that. If the initial attacks on a lot of the Blu-ray players and a lot of the AES players and other devices happened because people were able to just sift through the RAM and find the password. This has also been the way that a lot of video game players have been broken, where they just sorted through the RAM, found the place in the RAM where the password lived, and then just pulled it out. So, just a simple example. You've got AES, you've got something that you want to encrypt, you've got a key that goes in, it's the same key every time, and you run it through the black box, and you get some ciphertext output, right? So if I've got, say, a picture, and I want to encrypt a JPEG file, and I want to encrypt the JPEG file so that nobody knows what's in the JPEG file, how many people think this would be a secure method? AES is bulletproof, I'll tell you that. The best attacks to date have only been able to peel off a few bits of security, so the problem is not here. Well, if you start with an image like this, and you use the method I just showed you, that's what you get. Because when you take a block of, say, you've got a string of zeros, and you take that string of zeros and you encrypt it with the same key over and over again, it's going to look the same, right? Because this transformation is very repeatable. Same key, same plain text, you will get the same ciphertext. So that allows you to look at patterns. But if you use a mode that looks more like this, where you put in a randomization value, sorry, the lines did not come out on this one. What you're supposed to see is a line that comes and feeds back the crypto text up here. So this initialization value changes every time, and you get a different input to the block cipher each time. And that value is unpredictable. Oh, there are lots of modes. You should be very careful using ECB. Yeah, pardon me, rented lips. The comment was you should not use ECB as a finished cipher for encrypting secure data. And I would say yes, the answer is that ECB, the basic AES block, is more of a component that you should put together with other things. So I'm going to go ahead and skip the last example, but basically the message I was trying to convey is that if you really want your system to be secure, you have to think about it as you're building it. You can't just build the whole thing and then bolt on some security afterwards. And this is even more challenging in a pure software environment because you don't have a secure core that you can go back to. In an embedded system where or like a smart card, you can buy a crypto core. If you incorporate that and use that properly, then you've got something that's pretty good. In a software environment where the adversary may have access to your full memory space, it gets quite a bit more challenging. Okay. There were some attacks used remotely on smartphones. You may see more of this. There's also been some speculation that the radio used for traffic, in other words, when you're talking on the phone, the radio that gives you the voice connection has power modulation based on the strength of the battery. And because of the way batteries work, the greater the load on the battery, the less voltage it provides. there's been some speculation that that signal could also be used to do this kind of an attack. And the message that we heard earlier was, don't try to do crypto yourself. You will almost certainly fail unless you're already an expert. There are too many implementations that have been done well, so I strongly recommend that you copy an implementation that's been done sufficiently as opposed to trying to invent one yourself. And even very small mistakes can be exploited to provide a backdoor that completely defeats your security. So I hope you found that interesting. Sorry it was a little bit more esoteric than you probably bargained for.